In this lesson, I'm going to show you where all of the index laws come from, and I'm also going to show you how to use them. Before starting, I should tell you what an index actually is. Just like multiplication is repeated addition, an index is repeated multiplication. So over here, I've written 3 to the power of 4. We write this by writing the 3 at the bottom, and then we write the 4 up the top. The 4 at the top is what we'd call the index, and it tells us how many times we need to multiply 3 by itself in order to produce our answer. So if I write 3 to the power of 4, that's the exact same thing as 3 times 3 times 3 times 3 again. Now in order to come up with a whole bunch of rules for indices, we really just need to make one very simple observation. I want you to notice that when we write 3 to the power of 4, it's 3 times 3 to the power of 3, because 3 to the power of 3 is just 3 times 3 times 3. This allows us to make two really important conclusions that are going to serve almost like the definitions of an index for us. The general idea is that 3 to the power of 4 is going to be 3 times 3 to the power of 3. Or we could even think of this in another way. If you started off with 3 to the power of 4, if you then divided by 3, you'd end up with 3 to the power of 3. So if you divided by 3 here, this 3 and this 3 would cancel, and you're only left with 3 to the power of 3. Now you can look at either one of these two as the definition of an index, because you can use either one of these to actually come up with any of the index laws that we're about to show you. So for example, to go from 3 to the 4 to 3 to the power of 3, we just have to take 3 to the 4 and divide by 3. So this part over here is 3 to the 3, as we said. But then you can see something else here too. Notice that this over here is the same thing as 3 to the power of 2. So that immediately tells us that 3 times 3 to the power of 2 is the exact same thing as 3 to the power of 3. So that just means that if you start with 3 to the power of 3, and then you divide by 3, you can cross out the 3's and you're left with 3 to the power of 2. And then we could just repeat the same process. 3 to the power of 1 would just be 3 because you could take this term, divide by 3, these will cross out, and you're left with this. So this is going to be 3 to the power of 1. Now everything on this page should make at least some sense, I hope. 3 to the power of 4 is just 3 multiplied by itself 4 times. 3 to the 3, multiply 3 by itself 3 times. 3 squared, multiply it twice. 3 to the power of 1, multiply it by itself 1 time. But when you're learning maths, it's very rare that we see a pattern like this, and we decide not to keep going. So what would happen if we did keep going? You can see that we're going from 4 to 3 to 2 to 1. The next one on the list is going to be 3 to the power of 0, of course. What should that equal? Well, you notice to go from here to here, we divide by 3. Divide by 3 again. Divide by 3 again. Yeah, maybe we should divide by 3 one more time. So on the left, we can see that we just subtract 1 from the power, because that's what we've been doing this whole time. But on the right, we should just be dividing by 3. So if we divide by 3, then 3 divided by 3 just crosses the 3's out, and you're left with the number 1. So that means 3 to the power of 0 has to be 1. Now in the normal way this is said, it seems to make no sense. 3 to the power of 0 is 1 means that if you multiply 3 by itself 0 times, you get 1. But if you really think about it, it actually does make a fair bit of sense. 3 to the power of 4 can be thought of as 1 times 3 times 3 times 3 times 3. 3 to the power of 3 can be thought of as 1 times 3 times 3 times 3, and so on. Well then that means 3 to the power of 1 is just 1 times 3. If we divide by 3, then we just get these to go away, and you're left with the number 1. And by that logic, there's really no point in stopping here. We can keep going. How about we divide by 3 one more time? We'll see that if you got 4, 3, 2, 1, 0, the next number in the list is going to be minus 1. So let's write 3 to the power of minus 1. Then on the right hand side, we just need to remember to divide by 3 again. So that means 3 to the power of minus 1 is the same thing as 1 divided by 3. Usually, we'd call this 3 to the power of minus 1 the reciprocal of 3. And you can get the reciprocal of a number just by flipping it upside down. And by flipping it upside down, I mean writing it like this. Now of course, nothing is really forcing us to stop here. We could continue dividing by 3 to our heart's content. And you can also multiply by 3 to keep going up this list as well, so you can multiply by 3 to get to 3 to the power of 5. But in either case, I think these basic examples illustrate the general idea. Now there is one important point to make here. Is there anything special about this number 3? Well, not really. If I raise 3 to the power of 4, that's the same thing as raising 7 to the power of 4. I just replace all of these 3's for 7's. So instead of writing 3 or 7, I'm going to write the letter A, and A can be any number you like. Now instead of this over here being 3 to the power of 3, now it's actually A to the power of 3. And then instead of dividing by 3, we're actually dividing by A this time. So these two A's cross out to give you A to the power of 3. And then we could just repeat this all the way down the list. Let's replace every instance for 3 in the bottom for an A. And then I'm going to do this all the way down to the bottom of the list. Now this list is actually complete and it works for basically any number you like, but there is one exception, and that number is 0. You probably don't want to use the number 0 because to get from this step to this step, you're dividing by 0, right? So even if 0 to the power of 1 is going to be 0, if you try to divide by 0, then 0 to the power of 0 makes no sense. And indeed, 0 to the power of minus 1 can't be 1 on 0 because 1 on 0, again, doesn't make sense. In another video, I go into a lot more detail about why dividing by 0 makes no sense. If you'd like to figure out why, you can check that video. However, our two crowning jewels are still here. They still work just fine. A to the power of 0, no matter what A is always equal to 1. And A to the power of minus 1, no matter what A is always equal to 1 divided by A. At this stage, the only thing left is to really clean up these two definitions over here. We should say that A to the power of 4 is the same thing as A times A cubed. But it doesn't really matter that I chose this 4. So instead of choosing 4, I'm going to just choose a value, which I'm going to write as n. Now if this number over here is going to be n, then this number up here has to be 1 less than n, right? Because when we had a to the power of 4, we had a times a to the power of 3. If this is 4, then this is 3, and 3 is 1 less than 4. So the number that's less than n by 1 is just n minus 1. So I'm going to write n minus 1 over here. Okay, and when we say that 3 to the power of 3 is the same thing as 3 to the 4 divided by 3, we can rewrite this as a to the power of n minus 1 is the same thing as a to the n divided by a. Now many people, when they get shown these rules for the first time, get given them in these three forms over here. I tend to avoid these general cases when you're first learning, because you can always just choose a value of a to be anything you like, and you can always recover the old list that we had before. Now in the same spirit, there are actually a few more index laws to show you, but before giving you the general case first, I want to show you a specific example, and then we'll convert it into the general case just like we did before. Now our next index law comes by considering the expression 5 to the power of 4 times 5 to the power of 3. We know that 5 to the power of 4 is the same thing as multiplying 5 by itself 4 times. And then 5 to the power of 3 is the same thing as multiplying 5 by itself 3 times. So let's go ahead and make those substitutions. So we have 5 to the 4 over here, and 5 to the 3 is here. But if we look really carefully, these brackets aren't really serving any purpose. We're just going to be multiplying anyway, so let's get rid of them. And now we see that 5 to the power of 4 times 5 to the power of 3 just gives us 7 5's in total. So that's the same thing as 5 to the power of 7, because 4 plus 3 is the same thing as 7. So I hope you can see that when you multiply two expressions with indices and they have the same base, then you can just add the indices up to get the final answer. We can convert this into a general expression by replacing every instance of a 5 for an a. So I hope you can see that it would still be true that a to the power of 4 times a to the power of 3 is going to be the same thing as a to the power of 7. But mathematicians never stop there. Never, never. Instead what they do is they decide, let's go even further. What if this 4 was a random number like b? Well, let's go ahead and replace this for a b. Well, if you do that, then this bracket over here is no longer correct anymore. Instead of multiplying a by itself 4 times, you now need to multiply a by itself b times. And of course, if you're going to make this a b, then why is this 3 here? We might as well make that c. So instead of multiplying a by itself 3 times, this time we're going to multiply a by itself c times. Now, if you've multiplied a by itself b times over here, and then a further c times over here, then in total you've multiplied a by itself b plus c times. And then this gives us our index law. We can say that a to the power of b times a to the power of c is the exact same thing as a to the power of b plus c. So the general idea here is that a to the power of b times a to the power of c is going to give you the exact same answer as a to the power of b plus c in any case. And this is true for any values of a, b, and c. The only notable exception, of course, is a should not be 0, as we've said in the past. Now, instead of multiplying, our next index law comes from raising an expression with an index to the power of another index. Let me show you this. So in this case, we've started with 5 squared, and then we've decided to raise it to the power of 3. Well, let's ignore the inside for a moment, and just think about this. When you raise something to the power of 3, that's just the same thing as multiplying it by itself 3 times. So let's go ahead and do that. Let's multiply the inside by itself 3 times. Okay, so here we have 5 squared times 5 squared times 5 squared. So in this case, we can actually simplify this further. We know that 5 squared is the same thing as 5 times 5. So I can replace this in all 3 of these brackets. In this example over here, just like we saw in the last example, these brackets are serving no purpose. So we can go ahead and get rid of them as well. Now in this case, there are 3 brackets. And in each bracket, there are 2 5s. So you're basically multiplying 5 by itself 3 times 2 times, which is the same thing as multiplying 5 by itself 6 times. So the general idea is, when you've got 5 to the power of 2 raised to the power of 3 again, then you just multiply this 2 and this 3 together to get 6. And that's exactly what we see when we expand the brackets out like this. And of course, we wouldn't be doing maths if we didn't generalize this, so let's do that. First, we're going to replace this 5 for an a, just like we did before. So all of these 5s are going to turn into a's. And this is still perfectly true. A squared all to the power of 3 is just the same thing as a to the power of 6, because you just still multiply this 2 and this 3 together to get a to the power of 6. And you guessed it, we're going to keep going. I'm going to replace this 3 for a c. If we do that, rather than having 3 brackets, instead we're going to have c brackets. So we're going to multiply this a squared by itself c times. And to finish this off, rather than this being a squared, it could be a to the power of anything, so let's replace it for a to the power of b. So rather than having 2 a's in each bracket, instead you're going to have b a's in each bracket. Now in this bracket over here, I've multiplied a by itself b times. Then in this bracket, I've multiplied a by itself another b times. And then I'm going to repeat this c more times. So in total, I'm going to have b times in each bracket and then c groups of brackets. So that means I have b times c total a's. And therefore we can say that a to the power of b to the power of c is going to be the exact same thing as a to the power of b times c. Now these 5 rules over here are the basic rules that you need when you're dealing with indices. However, many people like to include one more rule on the list, and that occurs when you divide an expression by another expression with an index. However, personally, I don't give much importance to this last index rule, because you can get it directly from these 2. So for example, suppose we are dividing 5 to the power of 7 by 5 to the power of 4. Well, we could replace 5 to the 7 by 5 multiplied by itself 7 times, and 5 to the 4 by 5 multiplied by itself 4 times. Now the way this usually gets shown is that you can cross these 5s out like this, and then after doing this, you're left with only 3 5s at the end. And then we can say that 7 minus 4 is the same thing as 3. And it makes sense that we're subtracting because you just crossed out all of these 4 from the top and then you're left with 3. But instead of doing it this way, I like to take another approach. I've written a bit of a side note here. I want you to think about what 10 divided by 2 is. we could say that 10 divided by 2 is just 5 and leave it at that. Or in other words, what we could do is we could actually rewrite this as 10 times 1/2. Now this makes sense. You could say that 10 divided by 2 is just 5 because you're sharing 10 things amongst 2 people and each one gets 5, right? But another way you can think of it is that you start with 10 items and then you take half of it for each person. In either case, you're going to end up with the number 5 because half of 10 is always 5. But then we can use this rule over here. If we have 1 divided by 2, then a is 2, and we can rewrite this as the reciprocal of 2. We usually state this rule by saying that if you divide two numbers, that's the exact same thing as multiplication by the reciprocal. And then if we know that, it turns out that this division over here can easily be expressed in terms of these two rules that we already have. Now since we have 5 to the power of 7 divided by 5 to the power of 4, then we can rewrite this as 5 to the power of 7 times 5 to the power of 4, or reciprocaled. Okay, so if you look carefully at this part over here, you'll notice that it looks exactly like this, where b is the same thing as 4, and c is the same thing as -1. So that means 5 to the power of 4, all to the power of -1, is the same thing as 5 to the power of 4 times -1. But then we know that 4 times -1 is the exact same thing as -4. Now if you look again at this form over here, notice that this is exactly what we have. A is going to be the same thing as 5, B is going to be 7, and then C is going to be the exact same thing as -4. That means we can replace this whole thing for a to the power of b plus c, where b is 7 and c is -4. And then after this, we could just rewrite this as 5 to the power of 7 minus 4. If we wanted to, we could write this as 5 to the power of 3, because 5 to the power of 7 divided by 5 to the 4 is going to be 5 to the 3, as I've already shown. However, instead, we're going to just generalize this to get another rule that looks like one of these two. First, I'll replace every instance of a 5 for an a. Now, just like in the previous examples, this doesn't really change anything. Rewriting a for basically any number we want except 0 is just fine. The next thing we'll do is we'll replace the 7s for b's, and we'll replace the 4s for c's. So this brings us to the final form here. A to the power of b divided by a to the power of c is the same thing as this middle step, but it's also the same thing as a to the power of b minus c. So you just subtract these two indices to get this final answer. Now, a discussion on the index laws is not really complete unless we've done an example. So let me pull out an example and we'll work through it together. Now, I decided I'm just going to throw you right in the deep end here. So let's just work through this example together, and you'll see that if we just follow the rules, it's really not that bad. I'm going to start by actually copying it onto another line so that we can manipulate it. Okay, so for starters, if I see numbers that are not prime numbers, I always like to write them in terms of their primes. So for example, 4 is the same thing as 2 times 2, 6 is the same thing as 2 times 3, and 27 is the same thing as 3 times 3 times 3, or 3 cubed. After you've written every number in terms of its primes, there's actually a bit of an unsaid rule that I should probably show you before we go any further. So I've written a times b times c all squared. Well, I can rewrite that as a times b times c all times a times b times c. Now the brackets don't matter, so I'm going to get rid of them. And then I'm going to reorder everything. Let me put the a's together, the b's together, and then the c's together. Now after this, we can say that a times a is the same thing as a squared, b times b is the same thing as b squared, and c times c is the same thing as c squared. So this tells you that when you're multiplying a times b times c, and then squaring the whole thing, you can just square a, then square b, then square c individually. In fact, this is true no matter what this power over here is. It doesn't have to just be 2. It could be any number, so let me replace it for n. Now, I did this for the case where there are 3 things inside your brackets, but there don't have to be. You can have as many terms as you want inside the brackets, and the idea is that this n can just distribute to each one of the terms inside. Now we can apply this directly to this expression over here. Notice that in each of these brackets, there is a bracket with a few terms inside that we can distribute this 3 and this 2 into. Now that you've distributed this 3 to each of the terms here, and the 2 to each of the terms here, you end up with this expression here. To finish this off and to get it as simple as possible, you just want to use these two index laws here as much as you can to get the final answer. So for starters, you can see that 2 to the power of 2 all to the power of 3 can be simplified with this rule over here. 2 to the power of 3 is the same thing as 6, so we can replace that. We can also do the same thing over here. Now after this, I want you to notice that the brackets here and the brackets here aren't really necessary, so I'll get rid of them. And then this 3 to the power of 2 can just be rewritten as 3 squared. And then finally, you just want to remember that b squared all squared is going to be b to the power of 2 times 2, or b to the power of 4. I just noticed that I did a bit of a whoopsie here. I said that I was going to write everything in terms of its primes, but I forgot to write this 27 as 3 cubed, so let me replace it here, here, and over here. And now for my next trick, I'm just going to order the top and the bottom. I'm going to put all the 2's together, all the 3's together, then all the a's together, then all the b's together. Now after this, I'm going to multiply 2 to the power of 6 by 2 to the power of 2 using this rule over here. We know that this is going to turn into 2 to the power of 8. Then we also know that a to the power of 6 times a squared is also a to the power of 8. And b cubed times b to the power of 4 is also b to the power of 7, because 3 plus 4 is 7. Now to finish off, we've got some crossing to do. You can see that we can cross 3 squared out with 2 of the 3's over here, leaving us with only 1. After this, we can cross out 8 a's with 8 over here, leaving us with 2. Then finally, we can cross off 3 b's from this one over here, leaving us with 4. Now, we could say that we're done here if we like, but I can also rewrite 2 to the power of 8 now as 256. So let me just go ahead and write that. Okay, so after completing all these steps, we started with this huge expression over here. We wrote it in terms of its primes. Then we used this rule over here to distribute out all the brackets. And then after that, we used the index laws a few times. And then we can show that this thing is the exact same thing as this much smaller expression over here. Now there are many problems of this kind, and you can really make your own up as well. In general, anytime you have something like this where there are no additions and everything's just a multiplication or a division and a whole bunch of powers, you can generally simplify it and you can always write it as something like this. Usually a fair bit simpler, but not always. In general, you'll know you're done when you have only one instance of A and only one instance of B in your final answer, because everything else should have crossed out as long as there were no additions. So I think that just about completes our example. So I'd just like to summarize everything we covered in this lesson. In this lesson, we talked about the index laws. We said that a to the power of 4 is going to be the exact same thing as a times a times a times a. After this, we generalized the idea, and then we pushed it really far. We found that a to the power of 0, no matter what choice of a you have, is always equal to 1, and a to the power of minus 1 is always equal to 1 on a. However, I told you about a notable exception where a cannot equal 0, because you can't divide by a, and 0 to the power of 0 is really one of the things that make no sense. In fact, I call it the root of all evil. After this, we generalized further. We found that a to the power of b times a to the power of c is the exact same thing as a to the power of b plus c. And then we repeated the exact same arguments to show that a to the power of b all to the power of c is the same thing as a to the power of b times c. After this, we showed that division is the exact same thing as multiplication by the reciprocal. And then, by rewriting a division in terms of a reciprocal, we were able to use these two laws to show that a to the power of b divided by a to the power of c is the exact same thing as a to the power of b minus c. And then after this, we did an example and everything was great. However, there is one final side note that I'm going to leave you with here. I want you to notice that every single example we've done here has assumed that you have an integer in the power. Now an integer, in case you don't know, is just a whole number, like 4, 3, 0, or minus 1. But I'm asking this question. This is sort of my parting riddle for you. What should 2 to the power of 3.2 be? I mean, how would you even compute that? I mean, we know that 2 to the power of 3 is just going to be the same thing as 2 times 2 times 2. And 2 to the power of 4 is going to be 2 times 2 times 2 times 2. We'd expect 2 to the power of 3.2 to be somewhere between them, but how exactly do we compute its digits? So I'd like you to solve this little riddle of mine. I'd like you to figure out what the value of 2 to the power of 3.2 is without directly typing 2 to the 3.2 into your calculator. Is there any way you could do that? To be honest, when I first thought of this problem, it took me almost 2 years to solve it. Eventually I came up with a pretty convincing answer, and I'm going to show it to you in a future lesson. But if you'd like to think about it now, be my guest. It's a really fun think. But at that stage, I think we've just about said everything that needs to be said about the index laws. So that completes our lesson on the index laws. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.